Now, the world's largest nuclear fusion reactor has been switched on in Germany. It's used to fuse atomic particles together at extremely high temperatures.
Something just happened in Germany that has every energy company on the planet scrambling to reassess their strategies. An experimental reactor in a small town near the Baltic coast just shattered records that scientists thought were years away from being broken. We're talking about nuclear fusion, the holy grail of clean energy, and Germany just proved it's closer to reality than anyone expected. The implications, they're massive, and the timeline for commercial fusion power just got a whole lot shorter. The 43-second record that changed everything. In Greifswald, Germany, the Wendelstein 7X reactor, a massive machine that looks like something out of a sci-fi movie, held superheated plasma at fusion temperatures for 43 seconds. Now, 43 seconds might not sound impressive when you're waiting for your coffee to brew, but in the fusion world, this is monumental. Previous attempts at sustained fusion reactions typically measured in milliseconds or a few seconds at best. The reactor didn't just hit this duration, it maintained what scientists call the triple product, a combination of plasma density, temperature, and confinement time that determines whether fusion is actually viable. And the triple product is essentially the report card for fusion reactors. You need all three metrics firing on all cylinders simultaneously to achieve the conditions where hydrogen atoms smash together hard enough to fuse and release energy. Wendelstein 7X didn't just pass this test, it exceeded performance metrics that even tokamak reactors, the traditional gold standard design, have struggled to maintain for such extended periods. The Max Planck Institute for Plasma Physics, which operates the facility, confirmed that this run represents a fundamental leap forward in proving that sustained fusion reactions aren't just theoretically possible, they're practically achievable with current technology. What makes this even more remarkable is that the reactor operated continuously without the plasma destabilizing or collapsing, which has been one of fusion's biggest technical hurdles. When you're dealing with plasma hotter than the sun's core, we're talking 100 million degrees Celsius. Keeping it stable and contained is like trying to hold a miniature star in place with magnetic fields. For 43 seconds, Germany did exactly that, and the data they collected is now being analyzed to push even further. Why stellarators just beat tokamaks. Here's where things get technical, but stay with me because this matters. For decades, the fusion world has been dominated by tokamak reactors, donut-shaped machines that use powerful magnetic fields to contain plasma. Projects like ITER in France have invested billions into perfecting the tokamak design. But Wendelstein 7X is a stellarator, which is a completely different beast. Tokamaks are simpler to build but have a fundamental limitation. They require the plasma itself to generate part of the magnetic field through an electrical current running through it. This creates instabilities and limits how long you can maintain the reaction. It's like trying to drive a car that needs to constantly recharge its own battery while moving. Stellarators, on the other hand, generate all their magnetic confinement externally using twisted, complex coil arrangements. This means they can theoretically run continuously without the same limitations. The trade-off? Stellarators are nightmarishly complex to engineer. The magnetic coils have to be precisely shaped in three-dimensional configurations that look like they were designed by someone on heavy drugs. Wendelstein 7X has 50 superconducting magnetic coils, each one uniquely shaped and positioned with millimeter precision. Building this thing was one of the most complex engineering projects in history, but now it's paying off. The 43-second run proved that stellarators can maintain stable plasma for extended periods, something tokamaks still struggle with. For commercial power generation, you need continuous operation, not pulsed bursts. Germany just showed that their design philosophy might be the winning approach, and the rest of the fusion world is taking notice. The secret weapon: pellet injection technology. So how did Wendelstein 7X pull off this record? The answer lies in a new pellet injection system developed in collaboration with American researchers. During the 43-second run, the reactor fired approximately 90 frozen hydrogen pellets into the plasma at high speed. These pellets, each one essentially a tiny ice cube made of fusion fuel, continuously refuel the reaction, preventing the plasma from depleting and fizzling out. Think of it like feeding wood into a fire. Without continuous fuel, even the hottest flame dies. Previous fusion experiments struggled with this problem. They'd achieve high temperatures and density but couldn't maintain them because the fuel would burn through too quickly. The pellet injection system solves this by providing a steady stream of fresh hydrogen isotopes directly into the plasma core. The engineering behind this is genuinely impressive. You're shooting frozen pellets at supersonic speeds into a chamber where temperatures exceed the surface of the sun. The pellets have to survive long enough to reach the plasma core before vaporizing, and they need to be timed and positioned with extreme precision to avoid disrupting the magnetic confinement. Get it wrong, and the entire plasma destabilizes instantly. Germany's success with this technology represents one of those unsexy but critical breakthroughs that makes commercial fusion actually feasible. It's not flashy, but it's the kind of innovation that separates research experiments from working power plants. Germany's €2 billion bet on fusion dominance. The German government isn't treating this as a science experiment anymore. They're treating it as the future of their energy infrastructure, and they're backing it with serious money. The federal cabinet approved a comprehensive fusion action plan with over €2 billion in committed funding through 2029, with more than €1 billion specifically allocated to fusion research through 2028. This isn't just research grants, it's a strategic industrial policy designed to position Germany as the global leader in fusion technology. The action plan includes 8 fields of action covering everything from research infrastructure to regulatory frameworks. Germany is literally rewriting its radiation protection laws to create legal clarity for future fusion plants, because current nuclear regulations were written for fission reactors and don't really apply to fusion. What does €2 billion buy you in fusion research? It funds new experimental facilities, supports a growing ecosystem of startups and private companies, builds supply chains for specialized components like superconducting magnets and plasma-facing materials, and trains the next generation of fusion engineers and physicists. Germany is essentially building an entire industry from scratch, and they're moving fast. The political commitment is equally significant. This isn't one administration's pet project, it's bipartisan support with backing from across the government coalition. Energy security has become a paramount concern for Germany, especially after recent geopolitical disruptions to natural gas supplies. Fusion offers a path to true energy independence, nearly unlimited fuel supply from abundant hydrogen isotopes, no carbon emissions, minimal radioactive waste compared to fission, and no dependence on foreign energy suppliers. Germany is also positioning this as a jobs program. The fusion industry will require advanced manufacturing, specialized engineering expertise, and cutting-edge research facilities, all areas where Germany already excels. By dominating fusion technology now, they're setting themselves up to export reactors and expertise globally once the technology matures. Startups racing to build the first commercial reactor. While Wendelstein 7X is proving the science works, a new generation of German startups is racing to commercialize it. Companies like Gauss Fusion, Proxima Fusion, Marvel Fusion, and Focused Energy are attracting hundreds of millions in investment and pushing aggressive timelines that would have seemed absurd just 5 years ago. Gauss Fusion recently unveiled Europe's first complete design for a commercial fusion power plant. Their plan calls for a €15 to €18 billion first-of-a-kind reactor that would come online in the mid-2040s. Yes, that's an astronomical price tag, but it's an actual blueprint with engineering specifications, not a vague concept. They're calling it the Eurofighter for fusion, deliberately invoking Europe's successful military aircraft consortium as a model for pooling industrial capacity and investment across multiple nations. The design leverages stellarator technology similar to Wendelstein 7X but scaled up for power generation. Gauss Fusion estimates their reactor would generate baseload electricity continuously, solving one of the major criticisms of renewable energy sources. Solar and wind are great, but they're intermittent. Fusion would provide constant, reliable power regardless of weather or time of day. Proxima Fusion, another Munich-based startup, is pursuing what they call a quasi-isodynamic stellarator design, basically an optimized version of the W7X concept with improvements based on recent experimental data. They've attracted significant venture capital funding and are working toward demonstration plants by the early 2030s. Their timeline is aggressive, maybe even unrealistic, but that's how breakthrough industries work. Lots of bold bets, some failures, and a few spectacular successes. These startups are collectively calling for €3 billion in public funding to accelerate development of pilot plants by 2030. Their argument is simple: the science is proven, the engineering is feasible, and now it's a question of scaling up and demonstrating commercial viability. Germany's government seems to be listening. The Biblis nuclear site's second life. In a move rich with symbolism, Germany is planning to build a 1-gigawatt fusion pilot plant at Biblis, the site of a decommissioned nuclear fission reactor. This location choice is deliberate and brilliant for multiple reasons. First, the infrastructure is already there. Biblis has grid connections capable of handling gigawatt-scale power output, cooling systems, trained personnel familiar with nuclear operations, and regulatory approval for nuclear facilities. Building on a brownfield site instead of starting from scratch saves enormous amounts of time and money. Second, the symbolism is powerful. Germany famously shut down its fission nuclear program after Fukushima, committing to a renewable energy transition. But renewables alone haven't been enough to meet Germany's industrial energy demands while phasing out fossil fuels. Fusion offers a middle path: the energy density and reliability of nuclear power without the long-lived radioactive waste and meltdown risks of fission. Building the fusion plant where fission reactors once stood sends a clear message: this is the new nuclear, and it's nothing like the old one. The Biblis project also leverages an existing, skilled workforce. The technicians, engineers, and operators who worked at the fission plant have transferable expertise. Many of them are still in the region and would welcome employment in next-generation nuclear technology. Germany gets to repurpose not just infrastructure but human capital. The 1-gigawatt capacity target is significant. That's enough to power a medium-sized city. If the pilot plant succeeds, it would prove commercial viability at a scale that matters for national energy policy. This isn't a small research reactor, it's a demonstration that fusion can contribute meaningfully to the grid. Why this terrifies traditional energy giants. If you're running a fossil fuel company or even a renewable energy corporation, Germany's fusion breakthrough should keep you up at night. Here's why. Fusion potentially obsoletes entire industries while creating entirely new competitive dynamics in energy markets. For oil and gas companies, fusion represents an existential threat. These corporations have spent decades building extraction infrastructure, refining capacity, and distribution networks worth trillions of dollars. Fusion offers abundant energy from fuel sources that are effectively unlimited. Deuterium can be extracted from seawater, and tritium can be bred within the reactor itself. No more geopolitical dependence on fossil fuel reserves, no more price volatility from supply disruptions, no more drilling operations. The entire business model becomes obsolete. Even renewable energy companies face disruption. Solar and wind have dominated the clean energy conversation for years, attracting massive investment and government subsidies. But they have inherent limitations: intermittency, land use requirements, and the need for expensive energy storage systems to provide baseload power. Fusion offers 24/7 generation with a tiny physical footprint. A single fusion plant could replace dozens of wind farms while generating power continuously regardless of weather conditions. The utility industry faces potential restructuring. Current grid infrastructure is designed around centralized fossil fuel plants and increasingly distributed renewable sources. Fusion could shift the paradigm back towards centralized generation, but with clean fuel and minimal waste. Utilities that pivot quickly and invest in fusion partnerships might thrive. Those that cling to legacy technologies could find themselves obsolete. There's also the manufacturing and supply chain angle. Industries that have built businesses around wind turbines, solar panels, batteries, and grid storage could see demand plateau if fusion scales quickly. Meanwhile, entirely new industries around superconducting magnets, plasma diagnostics, tritium breeding, and specialized materials would explode. The smart money is already hedging. Major energy companies are quietly establishing fusion research partnerships and making strategic investments in fusion startups. Nobody wants to be the next Kodak, dominant in film cameras right when digital photography emerged. The global fusion arms race heats up. Germany's breakthrough didn't happen in isolation, and it won't go unchallenged. The United States, China, and several other nations are pouring resources into fusion research, and Germany's success has intensified the competition. The US has seen an explosion of private fusion companies backed by Silicon Valley capital. Commonwealth Fusion Systems, TAE Technologies, Helion Energy, and others have raised billions in funding with timelines targeting commercial operation in the 2030s. The US Department of Energy is also investing heavily, viewing fusion as critical to energy security and technological leadership. Germany's achievement validates the entire fusion sector and will likely accelerate American investment. China is arguably the most aggressive player. The Chinese government has designated fusion as a strategic priority and is funding multiple parallel research programs. They're building massive tokamak facilities and investing in alternative fusion approaches, including laser-driven inertial confinement. For China, fusion represents both energy independence and technological prestige, a chance to lead in a transformative technology rather than play catch-up. The competition extends beyond national programs. The race is also about intellectual property, engineering talent, and supply chain dominance. Whoever perfects commercial fusion first will control patents worth trillions and establish technical standards that others must follow. There's also the export market. Once fusion is commercialized, nations will purchase reactors from whoever has the most proven, cost-effective technology. Germany's breakthrough forces everyone to accelerate. Countries that were planning demonstration plants in the 2040s are now reconsidering timelines. Research programs that seemed adequately funded now look under-resourced compared to Germany's commitment. The fusion arms race isn't military, but the stakes, technological dominance, energy independence, climate leadership are just as high. The 2040s timeline, realistic or hype? So here's the trillion-dollar question. Can Germany actually deliver commercial fusion power by the mid-2040s? Or is this just another round of overpromising from an industry famous for saying fusion is 30 years away for the past 50 years? The honest answer is that the timeline is aggressive but not absurd. Wendelstein 7X's 43-second run proved sustained fusion is achievable with existing technology. That's the science risk largely retired. What remains are engineering challenges. And engineering challenges, unlike physics problems, can be solved with sufficient money, talent, and time. The mid-2040s target assumes several things go right. First, demonstration plants in the 2030s need to successfully generate net electricity and prove continuous operation over months, not minutes. Second, materials science needs to deliver components that can withstand years of neutron bombardment and extreme thermal stress. Third, tritium breeding systems need to work at scale, because tritium is rare and has to be produced within the reactor itself for commercial viability. Fourth, costs need to come down dramatically from first-of-a-kind plants to make fusion competitive with other energy sources. None of these are insurmountable, but each represents real technical risk. History is littered with energy technologies that worked in the lab but failed at commercial scale. The difference this time is that the fundamentals are solid. Fusion isn't theoretical anymore, it's engineering. And when Germany commits €2 billion plus private investment, builds pilot plants, and creates regulatory frameworks, they're not messing around. There's also a self-fulfilling aspect to these timelines. Aggressive targets attract talent, investment, and political support, which accelerates progress. Conservative timelines lead to modest funding and slow development, which then validates the conservative timeline. Germany is betting that ambition breeds success, and their track record in engineering-intensive industries suggests that bet isn't crazy. Will the mid-2040s target hit perfectly? Probably not. Major infrastructure projects almost never deliver exactly on schedule. But 2040s versus 2050s is still revolutionary compared to the fusion is perpetually 50 years away narrative that's dominated for decades.